Imagine particles so elusive that they've remained undetected for decades. Yet, they may hold the key to unraveling two of the universe's biggest mysteries: dark matter and the enigmatic behavior of fundamental forces. These particles are known as axions. It may very well be that neutron stars, with their extreme environments of high gravity and magnetic fields, quietly produce dark matter. Now, this isn't just a wild theory. Researchers from Amsterdam, Princeton, and Oxford recently hypothesized that axions may not only exist, but could also accumulate around neutron stars in the form of massive invisible clouds. What's their significance? Axions could not only help explain dark matter, but they might also solve a long-standing problem in particle physics, the CP violation mystery. Due to their role in theories like string theory, axions have found themselves at the forefront of cutting-edge research. Neutron stars indeed act as axion factories. The implications for our understanding of particle physics and the structure of the universe could be immense. Axions aren't ordinary particles. In fact, you've likely never heard of them unless you've delved deep into the world of theoretical physics. Their story began in the 1970s, when physicists encountered a problem that didn't quite make sense: the so-called strong CP problem. Simply put, the laws of physics suggested that particles should behave in a way that violates charge parity symmetry when interacting through the strong nuclear force. This would imply that under certain conditions, neutrons should be able to change their charge and mirror orientation without returning to their original state. But experimental data showed the opposite. Neutrons remained neutral, hinting at a hidden symmetry. To solve this mystery, Roberto Peccei and Helen Quinn proposed an additional quantum field to clean up this symmetry problem, restoring theoretical balance in our understanding of neutrons. As often happens in quantum field theory, introducing a new field comes at a price. A new particle emerges, and so the axion was born, a hypothetical particle humorously named after a brand of laundry detergent because it cleaned up the strong CP problem. While the idea of an axion was originally put forward to solve the strong CP problem, it quickly drew the attention of cosmologists for another reason: dark matter. It's well known that dark matter makes up about 85% of the universe's mass, yet it has never been observed directly. Instead, we only see its gravitational effect on galaxies, bending light and affecting star movement. And this is where axions almost perfectly match the profile of a dark matter candidate. In the standard model, we know particles like photons, electrons, and quarks. These are particles we can observe and measure, but dark matter is missing from this list. At the same time, axions are theoretically numerous, incredibly light, and interact weakly with other particles, making them almost impossible to detect. What makes them especially interesting is that their interaction with electromagnetic fields, though weak, could leave noticeable traces. For example, the potential to convert into photons in the presence of strong magnetic fields. This is where neutron stars come into play. Their immense magnetic fields make them the ideal environment when searching for signs of axions. The connection between axions and dark matter isn't just theoretical speculation. Many dark matter candidates have been proposed over time, but axions stand out for addressing two problems simultaneously: the strong CP problem in particle physics and the dark matter mystery in cosmology. In recent years, serious efforts have begun to search for axions through experiments. Although their weak interaction with light makes them difficult to detect, by studying environments where such interactions are more likely, like neutron stars, scientists believe we may soon be able to observe them directly. Neutron stars are among the most extreme objects in the universe. Born from the violent death of massive stars, they have masses greater than our Sun but are compressed into a sphere only about 6 miles in diameter. Their density is staggering, and their magnetic fields are among the strongest in the universe, 1 billion times stronger than those generated on Earth. This extreme environment makes neutron stars more than just astrophysical curiosities. They become crucial laboratories for particle physics. One reason neutron stars are so significant for Axion research is their ability to act as natural particle factories. The intense magnetic fields around these stars, along with plasma discharges at their polar caps, create a high-energy environment. Here, axions could be produced in vast quantities. The process starts with the star's magnetic field. These fields, especially in a class of neutron stars known as magnetars, can reach 10 billion Tesla. For reference, the most powerful magnets on Earth produce only around 45 Tesla. In this immense magnetic environment, axions interact with photons, transforming back and forth between particles of light and matter. Plasma discharges occurring at the star's polar regions enhance these interactions. Plasma, an electrically charged gas, flows freely along the star's magnetic field lines, creating an environment where electric and magnetic fields interact intensely. These discharges produce pairs of electrons and positrons, and it's in these high-energy areas that axions are expected to emerge. The real key to axion formation in neutron stars lies in how these particles become trapped by extreme gravity. Axions produced at the star's surface might have a slight chance of escaping, but most will be gravitationally bound. Over time, they accumulate into what's known as an axion cloud, a dense region of axions surrounding the neutron star. Axion cloud formation is not an instant event. It's a process that unfolds over thousands of years. What makes these clouds especially intriguing is that they are forecast to reach densities far exceeding those we encounter in the dark matter halos surrounding galaxies. According to recent studies, axion density near the surface of a neutron star could exceed local dark matter density by more than 20 orders of magnitude. The buildup follows a well-defined evolutionary path divided into 4 phases: growth, saturation, spin down, and transient decay. Each stage reflects shifting dynamics within and around the neutron star, affecting how the axion cloud develops and interacts with its environment. The growth phase is the initial period of axion accumulation, which in theory lasts less than a year. During this stage, axions produced near the star's polar caps quickly fill the surrounding space. At this point, resistance to cloud formation is minimal, and the axion population grows rapidly. Next, the cloud encounters the saturation phase. This phase lasts thousands of years, during which the outer regions of the cloud begin interacting with the star's magnetic field through a process called resonant axion photon conversion. This interaction limits the cloud's growth in the outer layers, effectively capping axion density. However, the inner part of the cloud remains unaffected and continues to grow over time. As the neutron star ages, it transitions into the spin-down phase. At this stage, the star's rotational energy decreases, which in turn slows axion production. As a result, the cloud stops growing and starts to shift. As the star spins more slowly, its magnetic field weakens, and the region where axions interact with photons moves closer to the star's center. At the same time, the cloud becomes more compact, slowly releasing energy over time. Finally, the transient decay phase occurs at the end of a neutron star's life, when its magnetic field completely dissipates. At this stage, axion production ceases and the energy stored in the cloud is released. Scientists believe that depending on the star's properties, this could lead to a slow decay of the cloud or a burst of radio emissions, the latter being more dramatic. These bursts may last millions of years, or in some cases just a fraction of a second, depending on specific conditions. The final stage is particularly interesting for astronomers, since these bursts could potentially be observed with existing radio telescopes, offering a rare opportunity to detect axions indirectly. So what exactly could be the key to detecting such elusive particles? Theoretically, the scientist's approach is simple. As previously mentioned, axions interacting with a strong magnetic field can transform into photons, the phenomenon known as axion photon conversion. For neutron stars, especially magnetars where magnetic fields are exceptionally strong, this process becomes more likely. The resulting photons could be detected in the radio frequency range, giving astronomers a direct way to observe axion activity. However, these photons aren't emitted in a uniform fashion. They appear as specific signatures within the radio frequency range, and if we know what to look for, radio telescope data can reveal the presence of axion clouds around neutron stars. Predicted signatures include continuous faint emissions associated with the gradual accumulation of axions, as well as brief bursts of energy that may be linked to the rapid decay of these clouds. Despite promising theories regarding axion clouds, there are still significant challenges when it comes to direct detection. One major issue is the weak interaction between axions and light. The axion photon conversion process necessary to detect these elusive particles yields an incredibly faint signal, especially for low-mass axions. This faintness complicates the task of isolating axion signals from the universe's background noise. Additionally, current radio telescopes, though powerful, aren't sensitive enough to detect the extremely low-energy photons that may result from axion conversion. Another limitation lies within the theoretical model themselves. Although researchers have made progress in predicting axion behavior, major parts of the theory are still in development. Different models predict a wide range of possible masses and interaction strengths, leaving a broad parameter space for exploration. This means that even if axions do exist, we may not be searching within the right frequency range or looking for the correct observational signatures. Nonetheless, the search for these signals is well underway. Modern radio telescopes such as Parkes in Australia, Green Bank in West Virginia, and Arecibo in Puerto Rico have collected data over decades, and this archival information has become a treasure trove for axion hunters. For now, no precise axion signals have been detected. However, the sensitivity of these instruments have allowed scientists to rule out certain particle mass ranges and interaction strengths. This means that while nothing has been found yet, the window in which axions might exist is becoming more narrow. So what exactly are astronomers looking for? Signals may take various forms. Continuous radio waves emitted by axion clouds would appear as faint, persistent sources in the data, distinguishable from other types of stellar noise. However, even more intriguing are transient events, bursts of light that could occur when axion clouds dissipate or interact with the weakening magnetic field of an aging neutron star. These energy bursts, though rare, might even be related to fast radio bursts, mysterious high-energy radio flashes that have puzzled astronomers for years. The question is no longer whether axions can be detected, but when and how we'll detect them. Looking ahead, the development of new radio telescopes brings us closer to unlocking this mystery. For example, the Square Kilometer Array, or SKA, promises to revolutionize axion research. Thanks to its immense sensitivity and unprecedented ability to scan large portions of the sky, the SKA will be able to detect the faint hum of axion photon conversions, or brief flashes produced by dissipating Axion clouds. Other future instruments, such as the Next Generation Very Large Array and the LOFAR 2.0, will add more layers to the hunt, focusing on different parts of the radio spectrum and extending the boundaries of detection. These future telescopes will search not only for continuous emissions from neutron stars, but also for elusive transient bursts, which could ultimately confirm the existence of Axion clouds. In the coming decades, as theoretical models are refined and observational data becomes more precise, we may be on the brink of a major discovery. The implications of detecting axions or even narrowing the bounds of their possible existence are enormous. If these particles form part of dark matter, as many theories suggest, they could help bridge the gap between particle physics and cosmology. While it's likely that neutron stars generate axions, the numbers alone won't explain all the dark matter we seek. To fully account for dark matter, we'd need far larger quantities. However, even if axions represent only a portion of dark matter, detecting them near neutron stars would be groundbreaking, offering a direct pathway to studying how dark matter interacts with extreme environments. And while many questions remain unanswered, the potential rewards are vast. Discoveries that could transform our understanding of both dark matter and fundamental physics. Either way, the mysteries of the universe won't unveil themselves, and perhaps the next breakthrough lies within the quiet signals of a distant star. Today we'll delve deeper into the study of a phenomenon that is both violent and vital in the grand cosmic plan, the collision of planets. The cataclysms in which planets collide and merge are not just spectacular shows of cosmic fireworks. They are the architects of worlds, the creators of moons, and perhaps the creators of life itself. It is here, amidst the chaos of colliding worlds, that we find the solution to our planet's past and the mysteries of other solar systems. Our story begins about 4.5 billion years ago, with the colossal impact that gave birth to the Earth and its faithful companion, the Moon. Imagine two similar planets in the same orbit, pulled together in a cosmic embrace. This grand collision not only formed the Earth-Moon system, but also set a precedent for understanding the formation of planets in the universe. Recent astronomical observations thousands of light years away have recorded a similar but much more dramatic event. Two giant planets like Neptune collided at astonishing speeds. This collision was so powerful that it caused the light of their own star to be attenuated by a staggering 95%. Such observations make new adjustments to our understanding of cosmic events and indicate that planet collisions may be far more common than previously thought. From the birth of satellites to the mysteries of planet formation, today we'll witness the power of gravitational entrapment, unravel the history of our Earth and Moon, and look into the future of space exploration. Across the vastness of the universe, the birth of satellites is a tale of cosmic creativity. Satellites, or moons as we often call them, are born in many different ways, each telling a unique story of celestial mechanics and cosmic chance. One of the main ways in which satellite formation occurs is within the circumplanetary disk. This disk, composed of gas, dust, and debris, orbits around young planets like a miniature solar system. Over time, the material in this disk coalesces, giving birth to moons. The classic example is Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. These moons form from the same disk that surround Jupiter when it was young, a process mirrored in miniature throughout our solar system. Another intriguing challenge is gravitational entrapment. This event occurs when a wandering celestial body, attracted by a planet's gravity, becomes trapped in its orbit. Neptune's moon Triton is a prime example of this. Astronomers believe that Triton, with its retrograde orbit, was captured by Neptune's gravity, and now the interplanetary vagabond is locked in endless tandem with its host planet. Finally, we explore the third, a violent but creative process resulting from the collision of giant planets. This scenario resembles a celestial race for survival, where the consequences of such colossal collisions can lead to the formation of moons. The origin story of our own moon is believed by many scientists to be the result of such a cataclysm. About 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. The debris from this massive collision eventually coalesced to form the moon, our permanent satellite. Each of these processes, formation in the near-planetary disk, gravitational entrapment, and the consequences of planet collisions, provide evidence for the dynamic and often tumultuous history of planet formation. Let's take a closer look at the thrilling spectacle of gravitational entrapment. The very process when a celestial wanderer drifting in space is captured by the gravitational pull of a planet, changing its fate forever. One of the most intriguing examples of this cosmic phenomenon is Neptune's largest moon, Triton. Unlike most moons in our solar system, Triton orbits Neptune in a retrograde direction, a clear sign of its dramatic past as a captured object. This unusual moon, with its icy surface and thin atmosphere, was likely a free-floating object in the Kuiper Belt before Neptune's gravity drew it into orbit. The Kuiper Belt is the region of the solar system beyond the orbit of Neptune. Although the Kuiper Belt is similar to the asteroid belt, it's about 20 times wider and 10 times more massive than the latter. The secrets of Triton's capture are not limited to its orbit. The event had a profound effect on both Triton and Neptune itself. The capture resulted in enormous tidal forces that altered Triton's internal structure and may have given rise to its geologic activity. In addition, it may have altered Neptune's orbit and axis of rotation. Capturing Triton is not only the story of the moon, but also a window into the composition and evolution of celestial bodies in the outer solar system. By studying Triton, scientists can gain insight into the composition and characteristics of other Kuiper Belt objects. Its icy surface, with its nitrogen geysers and thin atmosphere, provides insight into conditions in this distant region of our system. The implications of Triton's capture extend to our understanding of planetary systems beyond our own. Such events can dramatically change the dynamics of a planet's moons and rings. This shapes our understanding of how satellite systems evolve and influences the search for similar phenomena in exoplanetary systems. Now let's move closer. As we've already mentioned, the Earth holds the secret of a turbulent and pivotal past, a secret it shares with its closest celestial partner, the Moon. The story of their birth is a story of cataclysm and creation, which determined the fate of both bodies as a result of a monumental event, the collision of planets. According to the giant impact hypothesis, about 4.5 billion years ago, a Mars-sized body called Theia collided with the young Earth. This colossal impact was not just an impact, but a catastrophe whose energy was enough to melt and vaporize both Theia and much of Earth. After this cosmic cataclysm, a disk of debris consisting of parts of Theia and Earth revolved around the molten planet. Over time, these fragments fused together under the force of gravity, giving birth to our moon. The Earth, too, was forever changed. Its composition, axis, and orbit were altered by this collision. The evidence supporting this hypothesis lies not only in theoretical models, but also in tangible evidence. Samples of lunar rocks brought back by the Apollo mission are strikingly similar in composition to Earth's mantle, suggesting a common origin. In addition, computer modeling of this event accurately matches the current orbital dynamics of the Earth-Moon system. This theory has profound implications for understanding the history of the Earth itself. The impact probably played a crucial role in shaping the planet's geology and probably even its ability to harbor life. By stripping the Earth of some of its primordial atmosphere and altering its rotation, the impact may have laid the groundwork for the unique conditions that support life as we know it. Thus, when we look at the Moon, we are looking not just at a satellite of the Earth, but at a part of our planet's past, a celestial body born out of one of the most dramatic events, at least to us, in the history of our solar system. Among the accounts of the formation and evolution of our cosmic neighbor are other, often overlooked consequences of planetary collisions. These events not only shape the planets and their moons, but also leave behind characteristics and phenomena that further define the character of these celestial bodies. One such consequence is the formation of planetary rings. These beautiful and delicate structures that often adorn gas giants such as Saturn may be the result of collisions. These rings, although not formed directly from a single massive collision, are believed to be the remnants of smaller and more numerous events, from tiny ice particles to large chunks of rock orbiting Saturn. These bodies create the iconic appearance that we see today. Such rings are not unique to Saturn. They are a common consequence of collisions in planetary systems. Another intriguing result is the tilt of the planet. Uranus, with its peculiar axis of rotation, is a prime example. Astronomers suggest that a massive collision with an Earth-sized object in the distant past may have flipped the planet on its side, resulting in its extreme axial tilt of about 98 degrees. This tilt accounts for the planet's incredibly contrasting seasons and unusual magnetic field. Coming closer to home, Mars presents another intriguing case study. The Borealis Basin, a huge impact crater that occupies most of Mars' northern hemisphere, is thought to be the result of a colossal impact. The red planet also has a smooth, flat northern hemisphere, in stark contrast to the heavily cratered southern hemisphere. The dichotomy suggests that a powerful impact occurred in Mars' past, altering its surface and possibly also affecting its internal dynamics and subsequently the planet's climate and atmosphere. Even Venus, our sister planet, bears traces of a history of collisions. Its dense atmosphere, composed mostly of carbon dioxide with thick sulfuric acid clouds, raises questions about its past. Some theories suggest that comet impacts may have contributed to the dense atmosphere by delivering volatile compounds. These events may have created the greenhouse effect on Venus that led to the current inhospitable conditions. Each of these examples once again convinces us that even on such giant scales, collisions are far from rare. They continue to shape the physical characteristics, atmospheres, and even climate of planets, leaving an indelible legacy in their evolution. In the relentless pursuit of understanding the universe, astronomers have quite recently captured an amazing event: the potential collision of two giant planets. This unusual observation not only strikes our imagination, but also provides insight into the dynamics of planet formation and the evolution of stellar systems. Late last year, astronomers investigated observations made in 2021, an unusual phenomenon around the young star ASASSN-21QJ. This star, located about 1,850 light-years away, showed all the signs of such a grand event. The evidence? Significant infrared brightening and complex optical eclipse indicate a colossal planetary collision. The infrared enhancement of the star, corresponding to a blackbody temperature of 1000 Kelvin and lasting about 2.5 years, was superimposed on a wavelength-dependent optical eclipse lasting about 600 days. These observations led researchers to hypothesize the collision of two exoplanets, each with masses ranging from a few to tens of Earth masses, located at a distance of 2 to 16 astronomical units from the star itself. Such a collision is a spectacle of cosmic proportions. Imagine two planets, presumably similar to Neptune, being attracted to each other by gravity and colliding at high speeds. The consequences? A debris cloud that attenuates 95% of the star's light, and an incredibly hot, glowing remnant visible in infrared light. The significance of this event goes far beyond its awe-inspiring visual impact. It provides a glimpse into the rare processes that form young solar systems. These giant collisions, predicted by theories of planet formation, play a crucial role in determining the architecture of planetary systems. The study of ASA SSN-21QJ is a testament to the importance of continuous astronomical monitoring. Such observations allow us to record these fleeting but informative events, shedding light on the dynamics of planet collisions and their role in the formation of solar systems. Events occurring during the early and turbulent stages of stellar system evolution play a key role in shaping the characteristics of planets and moons. At the stage of the birth of a star system, space is a crowded, chaotic place. Planets, planetesimals, and debris are in constant motion, often colliding and merging. These collisions can lead to the formation of larger planetary bodies, changing their orbits, composition, and even atmospheres. Take our Earth, for example. Its collision with Theia not only led to the formation of the Moon, but also contributed to the tilt and speed of the Earth's rotation. This impact may have played a crucial role in the formation of Earth's stable climate, which eventually became the basis for life and our existence. The recent observation of the star system, ASA SSN-21QJ, emphasizes the significance of these events. This colossal collision provided a huge debris cloud. Following this discovery, it becomes more apparent that such events, while dramatic, are not rare anomalies, and at the same time form an integral part of the evolutionary narrative of stellar systems. Planetary collisions can have a variety of consequences. They can strip a planet of its atmosphere or promote its development, affect its magnetic field, and even determine its potential habitability. The moons from these collisions carry the legacy of their parent planets, providing clues about the history and evolution of the systems. Collisions also play a role in the redistribution of materials within the solar system. Elements formed at the heart of stars disperse and recombine, contributing to the diverse compositions of planets and moons. This cosmic recycling is fundamental to understanding the diversity of worlds we observe in our galaxy. We've already moved into a new era in astronomy, and the future of research and discovery in planetary collisions holds great potential. Continued advances in technology and ambitious space missions have the potential to revolutionize our understanding of cosmic events. Current and future research depends heavily on advanced observational technologies. Ground-based telescopes are becoming increasingly powerful and can detect even faint traces of distant collisions. Space telescopes, such as the James Webb Space Telescope, offer unprecedented views of the universe, providing deeper insights into the mysteries of planet formation and destruction. Future missions specifically designed to study exoplanets will further deepen our understanding. The goal of these missions is to obtain direct images of exoplanets, analyze their atmospheres, and even possibly detect evidence of past collisions. The data obtained will provide a better understanding of how planets form and evolve. Along with advances in observations, computational modeling is also undergoing a revolution. Supercomputers are now able to model complex planetary collisions with greater accuracy, helping us to predict and understand the outcomes of these events. These models, supported by real observational data, will play a crucial role in testing and refining our theories. The study of planetary collisions is a global challenge. Collaborative projects and international partnerships play an important role in pooling resources and expertise. Such collaborations not only advance our knowledge, but also inspire future generations of astronomers and scientists. In the grand narrative of the cosmos, planet collisions are far more than just spectacular events. They are the sculptors of worlds, the creator of moons, and shape the very characteristics that make each system, each planet, and you and I so unique. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground, beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering, but also of ambition, and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension, as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions in particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics, literally. By analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limit of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested, and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey did not end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped anti-hydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang theory suggests there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, a fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but also pushes the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider from a chain of small gas petals. Each proton began its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas petals, gaining energy at each stage until they finally arrive at LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, that energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well focused. The beams are carefully regulated or squeezed to ensure they collide in the detector at the point where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024. marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 teraelectron volts at even higher luminosities than before, meaning more collisions for data gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2202 mega electron volt, which agrees well with the predictions of the standard model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they have studied the behavior of the neutral D meson and neutral strange B meson, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomenon has been captured with unprecedented precision in recent data sets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into quark-gluon plasma. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the standard model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. Now, while the LHC can create tiny black holes, they are on the quantum scale and evaporate almost instantaneously through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. And finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, We want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multidimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. The ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our 3-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions at the LHC where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It is planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications to go far beyond particle physics, promising a glimpse into the very fabric of the cosmos and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time. Among the mysteries of the cosmos, the true titans of the universe are the stars. Imagine a star of unfathomable size and power, so huge that it eclipses our sun, making it a speck in comparison. Today we turn our eyes upward, not just to admire the beauty of stars, but to go in search of colossal, extraordinary, the largest stars known to science. Our sun, the heart of the solar system, is just a speck of light against the backdrop of these giants. Stars so huge that they can encompass not only Earth or the inner planets, but extend beyond the orbit of Mars and in some cases even further. But what makes a star big? Is it mass, volume, or perhaps their effect on the surrounding cosmos? Our quest doesn't end with size alone. We'll look into the hearts of these giants, exploring the nuclear furnaces that fuel their glow and forces that may one day bring about their spectacular demise. Are you ready to explore the limits of the known universe and look into the heart of these space giants? Let us embark on a space journey that begins right here on Earth. Our planet, though conveniently just a speck in the grand scale of the universe, will be the starting point on the timeline. Now let's move on to Jupiter, the colossus of our solar system. It's not just another planet, it's a completely different beast. Jupiter is 11 times larger than Earth and 300 times more massive. Our first step toward understanding the vastness of the cosmos. Jupiter serves as a cosmic bridge from rocky worlds like ours to the gaseous worlds. It's composed mostly of hydrogen and helium, the same components that make up stars. It's not just a larger version of Earth, it's a fundamental shift in composition and characteristics, a formation that is beginning to take on the characteristics of the stars that light up our night sky. In cosmic science, mass and volume are key to understanding the difference between such giants and stars. Mass tells us about the gravitational power of an object and its ability to fuse elements in its core, determining its life cycle. Volume, on the other hand, gives us an idea of size and how much space this body occupies in outer space. These differences are fundamental to understanding the true nature of stars. It just so happens that the smallest mass of a gas cloud that can collapse to form some sort of star is about 1 Jupiter mass. It is at this mass threshold that we encounter a fascinating class of objects known as sub-brown dwarfs. These mysterious entities, often called rogue planets, are on the boundary between the largest planets and the smallest stars. They have the same composition of hydrogen and helium as Jupiter, but on a larger scale, at times leaning toward the deuterium burning mass that is the threshold for brown dwarf classification. However, sub-brown dwarfs lack the mass required for sustained hydrogen fusion, the hallmark of a true star, putting them at a cosmic impasse. With masses below the threshold required for thermonuclear fusion, they occupy a unique niche in the cosmic continuum for understanding the formation and evolution of celestial bodies. As we go deeper into space, we encounter the already mentioned brown dwarfs. These failed stars are interesting because they cannot sustain hydrogen fusion in their cores, a process that defines true stars. With masses ranging from 13 to 80 times that of Jupiter, they're much heavier than any planet, but they still lack the mass to ignite the nuclear fire that powers stars like our Sun. Because of this, they're in a cosmic limbo, glowing dimly from the heat of their formation, but never achieving the full nuclear fission that characterizes full stellar life. Moving beyond the realm of substellar objects, we enter the realm of red dwarfs, the most common and long-lived stars in the universe. These tiny stars mark the threshold beyond which stable hydrogen fusion begins, making them the main sequence stars that populate our galaxy in vast numbers. Red dwarfs are the founders of the cosmos, with lifespans of trillions of years, far surpassing the longevity of stars such as our Sun. Their longevity and abundance make them prime candidates for the search for extraterrestrial life, as their stable and long-lived nature gives enough time for planets in their habitable zone to potentially develop complex life forms. It is also interesting that these are the only main sequence stars that do not grow in volume when they die, but simply go out towards the end. Incidentally, the closest red dwarf to us, Barnard's star, is 5.96 light-years away, and is the fourth closest star to the Sun after the three components of the Alpha Centauri system. Its stellar mass is about 16% of the Sun's mass, and its diameter only about 1/5 of the Sun. Despite its proximity, the star is invisible to the naked eye. As we move away from the dim glow of red dwarfs, we reach the familiar warmth of our own Sun. The Sun, a main sequence star, is the baseline for understanding stellar magnitude. Its mass, brightness, and lifespan are the yardsticks by which we measure the true giants of the cosmos. With a temperature twice that of Barnard's star, the Sun shines several hundred times brighter than it. Moving on, we encounter Sirius, the brightest star in our night sky. Twice as massive as our Sun, its brilliance depends not only on proximity but also on its own luminosity. It shines 25 times brighter than the Sun. At this stage, relatively small changes in mass correspond to an unimaginable increase in the brightness of main sequence stars. However, by burning its materials so vigorously, the star shortens its lifetime by a factor of 4. The journey doesn't end there. Beta Centauri, a binary system, showcases stars whose masses are 10 times that of the Sun and whose surfaces blaze at unimaginable temperatures, 2.5 times that of Sirius. Such incandescence causes them to shine 20,000 times brighter than our Sun. However, possessing a rather impressive mass, scientists have diagnosed its lifespan at only 20 million years. Our journey through space brings us to the threshold of giants and hypergiants, stars that challenge the size limits of the stellar world. Hypergiants, larger than supergiants and giants, are rare stars that shine extremely brightly. By studying their enormous size, radiated power, and intriguing aspects of their measurements, we're discovering new information about the life cycles of the most massive stars in the cosmos. In a world of giants, UY Scuti, Stephenson 218, and WOH G64 are monumental figures, each embodying extreme aspects of stellar evolution. UY Scuti, a red hypergiant in the constellation Scutum, is known for its huge radius, making it one of the largest observable stars. Back in 1860, German astronomers from the Bonn Observatory first cataloged UY Scuti. A few years ago, this star gained lots of popularity as the largest star known to us. However, recent recalculation of distances has pushed it back down the list. The star is located near the center of the Milky Way, about 5,900 light-years from Earth. UY Scuti is nearly 800 times the size of our Sun. A star of this type loses most of its mass due to fast-moving stellar winds that take some of its materials with them. However, for all that, while remaining quite impressive, our candidate now does not even make it into the top 80 largest stars known to us. Stephenson 218, another red supergiant, thought to be the largest just a couple of years ago. The star's radius is estimated by some sources to be 2,150 solar radii. To make you realize the size, if you put the star in our solar system, Saturn's orbit would girdle its radius. And if you wanted to orbit it at the speed of light, one lap would take you an astonishing 9 hours. For example, the same trip around the Sun would only take 14.5 seconds. However, its luminosity is well above the Humphreys-Davidson limit, which we'll discuss later, and perhaps for this reason it's not a member of the Stephenson 2 cluster, which makes its location, as in the case of UY Scuti, closer, and consequently its size much smaller. So who actually takes first place, you ask? As of today, according to the list of the largest known stars, the leader is WOH G64. It has a radius of 1,540 solar radii. This means that if the star were at the center of our system, it would swallow the orbits of Mercury, Venus, Earth, Mars, and even Jupiter. This radius even fits within the stellar evolution limit, which we'll discuss next. Across the vastness of the universe, astronomers use state-of-the-art techniques to measure giant stars. One such method involves the use of spectroscopy, an instrument that analyzes the light emitted by stars. By decomposing starlight into its constituent colors, spectroscopy can determine the chemical composition, temperature, density, and relative motion of these celestial giants. This technique has played a crucial role in the study of WOH G64, revealing its enormous size and the intricate details of its surrounding dust envelope. Another innovative approach is interferometry, which combines the capabilities of multiple telescopes to model a larger aperture. This method greatly improves resolution, allowing astronomers to distinguish surface features and angular sizes of distant stars. The use of interferometry has led to breakthroughs in understanding stars such as UY Scuti and Stephenson 218, allowing us to understand their physical size and surrounding circumstellar material. Measuring the sizes of stars is difficult, primarily because of their vast distance and the complex structure of their outer layers. Such stars as WOH G64 are not only distant, but also shrouded in dense dust clouds, making direct size measurements difficult. The variability of these stars adds yet another layer of complexity, as their outer envelopes can expand and contract over time, changing their apparent size. In addition, the brightness and luminosity of these stars can lead to error in observations. The intense light can obscure the true edge of the star, making it difficult to determine where the star ends and the surrounding nebula begins. This ambiguity was a significant factor in the initial reassessment of the size of a large number of stars. The path to understanding these celestial giants also forces us to confront the stellar evolution limits in the Milky Way, often referred to as about 1,500 solar radii. This limit is related to theoretical limits on how large stars in our galaxy can become. The main factor determining a star's size and evolution is its mass. More massive stars have stronger gravitational forces that compress the core, resulting in higher temperatures and pressures. In the core, hydrogen atoms fuse to form helium, releasing energy in the process. This energy counteracts the gravitational force to collapse the star, keeping it stable. The limit of 1,500 solar radii is often associated with the Humphreys-Davidson limit, named after astronomers Roberta M. Humphreys and Chris Davidson. It denotes the region of the critical threshold on the diagram beyond which the luminosity of a star becomes so extreme that it can lead to its destabilization. In our case, it was an important milestone in the reassessment of the size of Stephenson 218. The initial classification of Stephenson 218 as one of the largest stars was called into question by its luminosity, which exceeded the Humphreys-Davidson limit. This paradox suggested that either our understanding of stellar physics needed refinement, or that the star's size was overestimated because of the difficulty of measuring such distant objects. It's also interesting that stars approaching or exceeding this limit experience significant mass loss due to a powerful stellar wind. The intense radiation pressure created by their extreme luminosity stimulates mass loss, forcing the star to shed its outer layers. Eventually, stars that have exceeded the limit of stellar evolution face an unsafe fate. When their core can no longer withstand the gravitational pressure, it rapidly collapses, leading to a cataclysmic supernova explosion. These explosions are some of the most energetic events in the universe. They scatter heavy elements into space, often leave behind compact remnants such as neutron stars or black holes. Exploring these limits highlights the delicate balance between mass, luminosity, and stability that allows these colossal stars to exist. It provides invaluable insight into the life cycles of the universe's most massive inhabitants. In the cosmic scene, size and mass often go hand in hand, but there are intriguing exceptions to this observation. It's natural to assume that the largest stars should also be the most massive, but the universe has a knack for refuting our expectations. This paradox is perfectly illustrated when we delve into the realm of colossal stars such as BAT 99-98. BAT 9998, a supergiant star, located in the large Magellanic Cloud constellation Doradus, boasts a colossal mass far beyond what we might expect based on its radius alone. With a mass of 226 solar masses, BAT 9998 is one of the most massive discovered to date, if not the most record-breaking. Despite the exceptional mass, the star is not remarkable for its large size. Its radius is 37.5 times that of the Sun, which corresponds to the size of a polar star, a white supergiant with a mass of 5.4 solar masses. However, as expected, both BAT 9998 and Polaris are not among the largest known stars. Residing in the Tarantula Nebula, a huge stellar nursery, it's among the most massive and brightest stars. BAT 9998 is rivaled by a close fellow Wolf-Rayet star, R136A1, located in the R136 cluster near the center of the Tarantula Nebula. As for the fate of such a star, BAT 9998, like many similar stars, is a candidate for supernova or hypernova. The exact outcome depends, of course, on the amount of mass lost. A supergiant may produce a gamma-ray burst and leave behind a neutron star or black hole, or it may not produce a visible supernova at all. In general, the life cycle of stars is quite intriguing. Stars begin their lives in the cold, dark corners of the universe in vast molecular clouds. These clouds, rich in gas and dust, serve as cosmic nurseries where gravity pulls the material together to form the heart of a new star. As the nascent star's core becomes denser and hotter, a dramatic transformation takes place. Nuclear fusion begins, turning hydrogen into helium and releasing a torrent of energy that lights up the cosmos. This fusion process is the star's powerhouse, the engine of its luminosity and heat. For stars like our Sun, this harmonious balance between gravitational forces and nuclear energy keeps them going for billions of years. However, this stage is only the beginning of their cosmic journey. As stars age, their fuel begins to run out. The Sun, for example, will undergo a dramatic transformation, becoming a red giant. This expansion is a paradox. Even as a star sheds its outer layers into space, it increases in size. becoming a huge, glowing ball of light that can engulf the inner planets of the solar system. But the life cycle of a star is not only a story of growth, it's also a story of loss. As the red giant phase fades, stars like our Sun shed those outer shells, forming ethereal structures known as planetary nebulae. The remaining core, stripped of its former glory, becomes a white dwarf, a dense, dim remnant of the star's heart. For more massive stars, the end is even more spectacular. Their demise comes in the form of a supernova, an explosion of unfathomable scale and beauty that eclipses entire galaxies for a brief moment. What remains may be a neutron star, or, if massive enough, a black hole. In this grand cosmic cycle, stars are not just points of light in the night sky. They are the forges of the universe, the creators of the elements that make up the world around us and within us. From their fiery birth to their spectacular death, stars are the architects of the cosmos, shaping the universe in their own image, one stellar life cycle at a time. Giant stars of enormous luminosity and size serve as cosmic beacons that illuminate the mysteries of the formation and evolution of the universe. By studying them, astronomers unravel the complex tangle of stellar life cycles, from the initial collapse of molecular clouds to the explosive finale of supernovae. The theoretical limits on the size of stars are still subjects of fierce debate among astrophysicists. However, in the realm of cosmic records, the title of largest star remains a dynamic prize. Discoveries and improved observational techniques are constantly revising the upper echelons of the stellar sizes. This fluid nature of space records once again emphasizes the vastness of the universe and the constant search for knowledge that drives our exploration of the cosmos. So, let's stay inquisitive as we eagerly await the discoveries that our universe holds.